Hello and welcome to Empowered Learning. This particular video will be the first video of the Set Theory Basics series. And so we first want to start off with doing the language of sets. So we want to find out what a set is and some of the basic things that we know about sets and how we actually use them to be able to help us solve problems. So let's go ahead and get started here. So the first thing that we want to know is that a set is called a collection of objects. And so a set contains or is made up of elements. And an element is also referred to as a member. So the point here is that when we talk about an element or a member, we're saying the same thing. Next, how do we represent sets? So the two most popular ways to represent a set is by expressing it in set builder notation, as well as using a Venn diagram. And so we'll talk about set builder notation now, and we'll talk a little bit about Venn diagrams, but you'll see that I have other videos that gives examples of how we actually take word problems and take that information and form it into a Venn diagram so that we can answer questions or analyze that situation better. And so we actually call those survey type problems. So once you're done watching this series of videos, I encourage you to check those out as well. So now that we know that the two most popular ways of representing a set here, of course, we want to make sure that we identify what is what. So set builder notation is a set that's actually described in terms of using these set braces here. And so we know that this would be the example of the set builder notation. And of course, a Venn diagram is just a diagram where we use circles to represent sets. So here this would be an example of what a Venn diagram would look like. Okay. So moving on here, how we would actually read our set builder notation, and I've just taken this example here. So we would read this as D is, and that's what equals means in math, is the set of, and so we would translate that as the set of all x such that, and that's what that line means. And sometimes you'll see when it's written like that, it'll also be written with a colon. Just depends upon who the author is in the textbook or how you learned it. So such that X is a student taking college math at State University. Okay. And of course, here this would be such that. So that line there means such that. All right. So moving on here, we'll see that one of the things that we need to know about sets is whether we actually know what's in them or not. And so the way that we say that a set is we actually know what's in it or not is we call it well defined. Okay. And so we say that sets are considered to be well defined if there is no confusion if whether a particular object or element is in the set. So another way I like to put this is, when I tell you what the set is, do you actually have a question that comes after that? Or do you say, yeah, I know who or what is exactly in that set? So I have these two examples here to sort of clarify that. So if we had a set B, and this set B is defined as the set of all Y, where Y is gross income earners over $250,000 a year. Now here, this one's pretty simple. Either you earn more than $250,000 a year or you don't. If you earn $250,000 and 1 cent, then you're in this set. If you earn $250,000 or below, you're not in that set. And it's pretty cut and dry. So because we don't have any questions after that, we exactly know who is in the set and who's not in the set, we will call this a well-defined set. Okay. On the contrary, we see that set W is an example of something that would not be a well-defined set. And we say that because W is a set of all M, where M is considered to be men who are weak. And so the question here is, what do you mean by weak? Do you mean weak physically? Do you mean weak mentally? Do you mean weak in intelligence? Do you mean weak at doing a particular job, or whatever? So you see how I have to ask all those questions. Um, since we don't know what weak actually means, then of course we know that this particular set is not well defined. Okay. All right, so moving on here, there is a set that exists that does not have any members in it. And this set is called the empty set, or it's also known as the null set. So some textbooks use empty set, others use null. They both mean the same thing. One notation for it is the circle with a line through it, and another one is the set braces that has nothing in between. And so both of those represent what we mean when we say a set with no members, basically. All right, so now in knowing that, we know that there's a difference in between having a set with no members and then a set that has a member, and that member is a set with no members. Okay, so here we see that this symbol here just represents the empty or null set, the set with no members, and of course this represents a set, which we're calling a normal set, with one member in it, and that member is the set with no members. And so as a way to try to explain what's going on here, I'm going to try out this example. I hope that it works. If it doesn't, then just kind of fast forward, okay? But I'm going to try. So imagine that we have a class of students that took a 9-question test. And so the test is divided up into 3 parts. And we know that no one in the class answered all 3 questions in part 2 of the test. We also know that no one answered the 3rd question in part 2 of the exam. So that means we know that for all the students who took the test, we don't know how many it is, but whoever took it, they only answered question 1, question 2, or answered questions 1 and 2 in part 2 of that exam. And of course, this class was divided up into 2 groups, a group A and a group B. Okay. So on the next page here, I'm going to kind of set that up for us. So let's say this is our test, and we got it broken up into 3 parts. 1, 2, 3, 1, 2, 3, and 1, 2, 3. Okay, and this is part 2, part 1, part 3. And of course, we had, we'll say this is our class here, and we broke up the class into 2 groups, which is A and B. So I'm going to define 2 sets here. Okay, so we're going to have a set X and a set Y. And so my set X is going to be the set of all, well, let's say all students. So let me change that right quick. Say all students in either group A or B that answered question 3, part 2. Okay? And so we're going to take Y and define that as all students who answered erase this, answered all questions in part 2. Okay? Now, here's the point that I'm trying to make here. So we know that all the students in either group A or B that answered question 3, we know that that has no members to it. So this would be equal to the null set. We also know that all the students who answered all the questions in part 2, that would be the null set as well. Now, we could kind of look at this and say that in a way, our set X here could actually fit inside our set Y. And so, of course, we can say that because if we look at this, set X is all the students in group A or B that answered question 3. And we know no one did that, right? But they're still a part of the same group of students who answered all questions in part 2, which is none of them as well. So the key part is students who answered questions in part 2, okay? So in a sense, we could come up with another set Z that could be said, all right, all students who answered questions in part 2 that came from either groups A or B that also answered question 3 in part 2. So if we looked at that, then we know that Z could actually be comprised of, or it could be comprised of X, or X could actually be a member inside of that set, how we actually defined it. And so because of that, if we wanted to keep it simple, which I'm going to do now, we could say that Y has several members in it, and one of those members is the set X, which is all the students who from either group B or group A that answered question 3 in part 2. Now, of course, we know that Y itself is the null set, but here we know that X is actually the null set as well. So we know that Y, if we look at it like this, it could have a member, and that member here is a subset of all the students who actually took the test and answered questions on part 2, but we know that they still didn't satisfy the requirements of answering all the questions. So that's kind of my way of coming up with an example with it. May not be the best, but I figured I'd try it out. If you like the example, comment and let me know. If not, then I'll just redo the video and try another one, okay? All right, so let's move on here. So now with Venn diagrams in particular, and remember our Venn diagrams kind of look like this, where we have our two sets here. We'll call this A, call that B. And for purposes of keeping it simple here, this U is what the universal set is. So we're considering everything here. So the universal set is the set of all elements, all members under consideration for a given discussion or situation. And so an example of that is, of course, I'm recording this video during the time where we have a major election cycle going on in 2016. And so, of course, if you are a citizen of the United States that's registered to vote, then you're in the whole set of, I guess, in the universal set, rather, of all people being considered as people that can vote for our next president, okay? And so here I just kept it simple here and just said that let U, our universal set here, be the set of all X, where X is a citizen of the U.S. And so, of course, anything that has to do with being a citizen of the U.S., the big universal set is all the people that are citizens, okay? So to make my point here, if we were talking about, people that were citizens of, let's say, Russia or Japan or Zimbabwe, something like that, then, of course, they would not be in our universal set anytime we talk about things that are purely for American citizens, okay? All right, so the next thing that we need to know about is what's called the element symbol. And so this is the mathematician symbol for how we say something belongs to a set or not. And so how I have here, we just say whatever's on the left, we say belongs to or is a member of what is on the right. And of course, when we put a line through it, that means that it does not belong. So as an example, and I'll do this quickly here, we see that 8 is a member of the real number set, okay? And that fancy R just means all real numbers. If we did something like this, 1 over 0, we know that that is not a legal real number. So we would say that particular number is not a member of the real number set. Okay. And as another example here, we see that 3 is a member of or belongs to this set here because we see it there. And of course, -5 is not a member because we don't see it here in our set there. Okay. All right, so moving on, the next thing that we want to talk about is the cardinal number for a set. And so when we talk about the cardinal number for a set, all that we're really talking about is how many elements are in that set. And sometimes it's referred to as the cardinality of a set. And so with that, we know that if a set is finite, its cardinal number is a whole number. And what we mean by whole number is numbers like 0, 1, 2, 3, so on and so forth. Okay. And of course, that's important because we actually need that number 0, because if we have a set that has no members in it, then its cardinality is 0. Okay. So that's why we're saying whole numbers instead of natural numbers. So if we have an infinite set, so for instance, like the set of natural numbers, we like to call these the counting numbers. So natural numbers are like 1, 2, 3, so on and so forth. It does not have a whole number as a cardinal number because, of course, there's an infinite amount of natural numbers that we can have. Okay. All right. So here we know that a cardinal number is either denoted by this or this. And so we see with the n and then a parenthesis with the set in there. And so this is like set A. We read this as the cardinality of A. And of course, it's also expressed in absolute value notation as well. And so it just depends upon what textbook you're using as to what way they actually express that, what way that they denote it. Okay. All right, so let's move on. All right, so to get some practice here, we have two sets. We have a set A and a set B. And here if we want to find out the cardinality of this set, since this set has 3 members, then we're going to say that the cardinality of that set A is just 3. And here for B, since we have 1, 2, 3, 4 members, then the cardinality of set B is going to be 4. All right, so now we need to talk about set equality and subsets. And so the first thing that we're going to tackle is this concept difference in between equivalence and equality. And so basically what I'm trying to say is there's a difference in between being equivalent and being equal within the world of set theory. To kind of give you a real world example of that, when we say something is equivalent in set theory, what we're actually doing is something like comparing 2 metropolitan cities. So let's say we wanted to compare, let's say let's just say Dallas-Fort Worth area and Houston metro area. Okay, so let's take those two since they're both in the state of Texas and they're fairly large metropolitan areas. So assuming that both metropolitan areas had about the same amount of people in it, we know that it doesn't, but we're just going to assume that. So if we were assuming that, then of course those 2 metropolitan areas would be equivalent because both metropolitan areas have similar things. So for instance, both metropolitan areas have a downtown area. They have an uptown area. They have an area that's actually within the city limits. And then they have the outskirts, so like the suburbs. Okay. They also have highways that go through them. And so for any major metropolitan area, you probably have, in the U.S. anyway, you have a major interstate highway that goes through it, and then you have some, what we like calling in Texas, spurs off of that. So for instance, in Dallas-Fort Worth, we have the interstate I-35, and then there is a loop around the actual city that is named I-635. Okay, so of course Houston has Interstate 10 and it has a loop around it called 610. So same kind of thing. So in that sense of how both cities sort of have some of the same properties, they are equivalent. Okay. The only way that the DFW area and Houston would be equal to one another is that if everyone that lived in Houston also lived in the Dallas-Fort Worth area. Now, of course, we know that that's not true, and so that's why we have the difference in between equivalence and equality. Okay. So to get to the definitions now, we see that if we have any two sets A and B, they will be equal if both of the following are true. First thing, sets A and B have the same cardinality, and I need to put same there. They have the same cardinality, okay? So in other words, they have the same number of elements in it. And so to me, this is like me saying that Dallas-Fort Worth and Houston both have the same amount of people, okay, in those metro areas. So the second thing is A and B have the same exact members. So in other words, whoever lives in Houston metro area also has to live in Dallas. So in order for those two metro areas to be equal in terms of set theory terms, that is what has to happen. Now, if any two sets A and B, they will be equivalent if each set has only the same cardinality, meaning that they just have the same amount of people in it. And so that's why I was saying in my example, let's assume that Dallas-Fort Worth and Houston metro areas have the same amount of people in it. And so because of that, since they have all these other properties that go on with it, they are considered to be equivalent in terms of set theory terms. Now, let's note that when the sets are equal, we can denote this by, of course, saying that A equals B. If the sets are not equal, then, of course, we know that we just put a line through the equal sign. Okay. All right, so for the next thing, we want to determine which sets out of the ones that are listed here are equivalent and which ones are equal. So we'll start with the equal first. So in order for sets to be equal, they have to have the same number of elements, and the elements have to be, each element in one set has to be in the other. And so if you see here, A and C fit that profile. Because, of course, 3 divided by 3 is the same thing as 1. 6 divided by 3 is the same thing as 2. And 9 divided by 3 is the same thing as 3. So A and C are equal to each other. Now, if we look at equivalence, equivalence just means that we have to have the same number of elements in the set. And if you notice, the cardinality for each and every set that we're talking about here is 3. And if you notice, B and D are different because the members in B are uppercase letters, whereas D are lowercase. So we can't call B and D equal. Okay? But we can say that all of these sets here are indeed equivalent to one another, since they all have the same number of elements. All right, so let's go ahead and move on to our next topic of talking about subsets. All right, so we're going to start talking about subsets here and proper subsets, but I want to first go ahead and kind of look at A and C again. So of course we know A is here, and this is what C was. And so this is asking us to show by definition of equality that the two sets are equal to one another. So of course, we know that the cardinality of A and the cardinality of C are the same. And we know that 3 divided by 3 is 1, 6 divided by 3 is 2, and 9 divided by 3 is 3. And so we have the same exact elements in each set. So that is how we can show by definition of equality that the two sets A and C are equal. Okay. Now, let's go ahead and talk about subsets right quick. So here, if we have given any two sets A and B, we know A is going to be a subset of B if every element in set A also shows up in set B. Okay, so if you see it in set A, then it should also show up in set B. And so by definition, that would make set A either have the same cardinality or a cardinality that is smaller than set B. Okay? And if we want to denote that, we would denote this by this symbol here. And so that is going to be our general subset symbol. Okay? Now, given any two sets A and B, A is a proper subset of B if both of the following are true. Number one, if A is considered to be a subset of B, meaning that everything that is in A also shows up in B. But we also see here that A can't equal B. And so what that actually means here in this sense is that the cardinality of set A has to be smaller than the cardinality of set B. So that's another way of saying it. Or there exists at least one element in B that's not also in A. And so by definition, that means that, let's say the cardinality of A is going to be less than the cardinality of B. Okay? And so from a visual standpoint, we could kind of look at this as saying, if we're going to be looking at something that is a subset of something else, we're going to have, in this case, the set A fit totally inside of set B. Now, I know I have it shown opposite here. And so what we would be saying in this case is something like that. So set B is a proper subset of A because all of B fits within A, and we'll probably have some extra members on the outside of B, but also in A. Okay. Now, let's consider this example here. So our universal set will be all the natural numbers from 1 to 10. We have A as being the natural numbers from 1 to 5. B is just being 2, 4, and 5. And C is 3, 2, 1, 4, and 5. Okay. So we see here that B is considered to be a proper subset of A and is a proper subset of C. And if you look at that, of course, B only has 2, 4, and 5 in it. And if you notice, A has 2, 4, and 5 in it, and C has 2, 4, and 5 in it. But you notice that here, 1 appears in A, but it doesn't appear in B. And of course, here, for C, 3 appears in C, but it doesn't appear in B. So that is why we say that B is a proper subset of both A and C. Of course, we also see that A and C are equal because, of course, both sets have 5 elements in it, and we also see that the elements that are there are the exact same. And so, of course, C is just the same thing as set A, is just rearranged a bit. So, but the arrangement of how the members come in a set does not matter. So in that instance, that's why A and C are considered to be equal. Now, last thing, we see that set A and C are not subsets of set B. And of course, they can't be because if you notice, the cardinality of A and C is larger than the cardinality of B. And so essentially, A can't fit into B and C can't fit into B. So that's why they're not subsets. All right, so now we want to make a connection here. So if we have two non-empty sets, A and B, they're related such that if A is a subset of B and B is a subset of A, then this implies that A and B are equal. So basically, what we're trying to say here is that if we're comparing two sets and they are subsets of each other, then that's another way of saying that the two sets are equal to each other. And of course, in just in case you forgot, a non-empty set just means that you have at least one member in that set. So we're saying that we want to consider set A and set B both having something in it. Okay. Now, of course, this would actually hold true for two sets that have nothing in it as well. But I just wanted to concentrate on the case of when it's non-empty. But any set that has no members in it is actually equal to the empty or null set. And of course, by definition, they will be equal to. Okay. All right, so now let's go ahead and do this practice exercise. And so what we want to do here is take the sets that we're given here. So this would be set A, set B, set C, set D, and we want to compare two of them at a time. And when we compare both of them, we want to say, is it a proper subset, or not a proper subset? And then we want to write that symbolic relationship. So we see for the first one here, we're comparing A and B here. So we see that A is a proper subset of B because, of course, B is just a set of all natural numbers, and A is just the first three natural numbers. So the cardinalities of these three sets are different, being that cardinality of A is smaller than B, but everything that is in A also appears in B. So that's why we have proper subset. We could express that this way. So this is a proper subset, but here we can also say that A is just a regular subset of set B as well, because that line that's under there, what that actually means is A can either be a proper subset or it could be equal to B. So that's really what that symbol means. When we say proper subset, we're getting very specific. Okay. All right. So now if we compare B to A, we see that since B is a set that has more members than A, then this will be not a proper subset. And of course, it's not actually a subset at all. So I'm going to put parentheses around there because we can say it's not a subset and it's not a proper subset either. And so, of course, that would look like this. We could do it like that, or if we wanted to, we could kind of do it with the line under it and do it like that. So either one of those would be acceptable. Moving on here, if we compare A and C, we see that A has 3 members, C has 2 members. So again, this is going to be not a proper subset. Okay. And here, just like how we did last time, we could do it like this, or we could do it like this. Okay. So for D and A, we see D has 1, 2, and 3, and A has 1, 2, and 3. So we see that in the context of what we're talking about here, D can be a subset of A. Now, we also see here that A and D are equal because they have the same number of elements in it as well as the same members. But for the context of this, we know that D is just going to be a subset of A. We also know that A is a subset of D. And so thus that makes those two sets equal to one another. Okay. And so, of course, now let's look at C and D. We see that C is going to be a proper subset of D because everything that is in C is also in D. But we see that the number 2 here appears in D but not in C. So this would be a proper subset. And so we could actually express this as C like that with the D. And we could actually call this just a regular subset too by definition. So we could just do that as well. Okay. And of course, comparing D to C going the other way, we know that that D is not a proper subset of C. Of course, we could express it the way that we have here, or we can do it with the line of that as well, and just say, well, actually, for D and C, yeah, we can just do it that way as well. Okay. All right, so let's go ahead and move on. Okay, so one of the things that we want to make sure that we illuminate here, that we got from the last example, is that any set can be a subset of itself. And so if you remember, we said that sets A and D were equal to one another because both of them had the same cardinality and the same members. And so here, of course, we could say here that A is a subset of D, and we can say D is a subset of A, and thus that makes A and D equal to one another. Okay, so we just want to illuminate that fact. So the next thing that we want to do is make sure that now that we've talked about subsets for a given set, well, how many subsets can we make of it? Okay, and so it's real simple to find this out. To find the number of subsets, we just take 2 and raise it to the power of k, where k is just the number of elements in set A, which is also what the cardinality of the set A is. So for example, our set A here with one triangle star, we see that we have 3 members there, so k would be 3. So if we take 2 and raise it to the third power, that would be 8. So it would have 8 different subsets. And so how we actually get these is we take all of our members here and form all the sets with just one element, and that gives us our first 3. And then we do the arrangements of taking these 3 members here and grouping them 2 at a time. And so that would actually look like these next 3. And then we would take, now that we've taken the members and group them 1 at a time and then group them 2 at a time, now we group them 3 at a time. Okay. The last one here is the null set. And so we know that for every set, we know that the null set is, theoretically speaking, a subset of it. And so the reason for that, I actually explain here below. And so I hope this particular explanation makes sense. Before I read this, one of the things that I need to state is that I'm borrowing something from logic to be able to figure this out. Okay. And so I'll start off with just a basic conditional statement here. So a conditional statement is written like this in logic. It says if P then Q. So let's say if we say if I drink a lot of water, then I'll have to go to the bathroom. Okay. Now, what we know from logic, that there are these logic statements that are called tautologies. And so basically they're equivalent statements, but they sound like they're not equivalent. And so one of the things that we know is that a conditional statement and a contrapositive statement are basically saying the same thing. Logically, they're equal. And so a contrapositive statement would be the negation of the statements but put in reverse. So if I said here, if I drink a lot of water, then I'll have to go to the restroom a lot. If I do the contrapositive, it says if I don't have to go to the restroom a lot, then that means I did not drink a lot of water. Logically, you're saying the same exact statement there, okay? And so I use this particular fact to help in being able to show how the null set is actually a subset of every set. Okay? And I'm just going to erase this here, and then we'll get going with the explanation. All right, so we know that the empty or the null set is expressed in this way. And so we're saying that it's going to be a subset, and so we want to ask why. So we want to recall that this actually means that it's a set with no members. And also, we want to know that for any two sets A and B, if we say that A is a subset of B, then every element that shows up in set A also has to show up in set B. Now, using that whole thing about the conditional and the contrapositive, I said, an equivalent way of stating if A is going to be a subset of B, then every element in set A is also in set B. We could also say that if every element not in set B is also not in set A. So I'm just taking the last part of this statement here and trying to state it contrapositively. Okay, and so if I read it all out, then it would say if every element not in set A is not in set B, then we know that A is not a subset of set B. Okay. And so here, if we let A be equal to the null set and B be any set, then any element that does not appear in B will also not appear in A, because remember, A has no members in it. So regardless of what shows up in B, there's not going to be anything from B showing up in A. Okay, and so contrapositively, we see that situation where if you had B being anything and A being the null set, it fits that whole thing of if B, if everything in B is not, well, say if every element in B does not show up in A, well, I read that wrong. So if any element in B does not show up in A, then that means B, well, A is not a subset of B. Okay, and so if we turn that around contrapositively, then that's actually telling us that A is going to be a subset of B. Okay, and so this is how this is sort of like a technicality here, but this is why we can say that the null set is going to be the subset of any set B here. And so the way that I describe it here is that if we let A be the null set and B be any set, then any element that does not appear in set B will also not appear in set A, since cardinality of set A is 0. It has no members in it. And so if we turn that statement around contrapositively, we say that A is a subset of B, which means that the null set is a subset of any set B. Okay, and so that's how we actually show that the subset of B, subset of that the null set is a subset of any set. Okay. All right, so I know this video was a little long, but this concludes the first part of the set theory basics. We'll continue on with part 2 of this particular series talking about set operations.